All right. We talked yesterday about these reflections that I want to give you a few more rules on some separate different types of lines that we can make reflections across. But we said if we're going to reflect across the x-axis, and if you can't remember these rules, guys, just draw a quick picture and say, okay, and put a point in the first quadrant. If you're going to reflect it over the x-axis, the way I always visualize it is reflection is after it's been conducted, symmetry exists. Does that make sense? So symmetry is the idea that there's what we call a line or axis of symmetry, which is something that you would fold on, and the one side will match up completely with the other side. Okay, so like our bodies have symmetry, right? Okay, now you've probably seen people do like they cover your left face or left side of your face up, and they cover up your right side of your face, and they talk about which side is prettier, or you look like a completely different person on one side of your face than you do the other side. They always argue that like people that are truly beautiful, they say have perfect symmetry, where the left side is identical to the right side, or they're as close to that as possible. So I have that perfect symmetry. But you can use use your line of reflection as that line of symmetry and think, okay, if this point is 2, 3, okay, and I fold on this, is the x value going to change? No. To still get to that point, I still got to move to the right from the origin 2 units. So the x value stays the same. But instead of going up, I'm going down now, right? So if 2, 3 was just any arbitrary ordered pair A, B, then this one would be A, negative B, right? So that can remind you of how, or I guess where the negative sign goes when you're trying to do this, okay? And then if I go to the y-axis, it's now negative A, positive B. Negative A, positive B, that the x value would change if I reflect across the y-axis, okay? There's some other lines that we want to reflect across. One of them is this line right here. Okay, does anybody know what the equation of this line is if it's going through 1, 1, 2, 2, 3, 3, 4, 4? It is up 1 over 1, so that's my slope, right? So my slope is 1. What's my y-intercept? 0. So slope is 1. Yep, so y equals x. Now think about this. Why is that the case? 1, 1. Does your y value equal your x value? 2, 2. Does your y value equal your x value? Okay, so y is x. If I want to reflect across that, okay, and reflection's distance is preserved. So what we're going to do is I'm going to try to take the distance from A to that line right there, which is going to be that distance right there. That will make it a dotted line. If I take that distance and reflect it across that line right there, it's still going to be perpendicular, okay? But kind of visualize where it's going to actually can reflect it. So if I were to fold on that line right there, that dotted line is going to go right there. And I'm going to get to a point called 5, 2. Does that make sense? Now, look at how 5, 2 and 2, 5 relate to each other. Let's move this point to there. 1, 4, 4, 1. Negative 1, 5, 5, negative 1, right? And if I trace this thing, let's trace that, and let's trace that. As I move this around, Okay, am I creating a reflection across that line? Does that make sense? Okay, but everywhere that point went, okay, just even there, is that x value now this y value? And is this y value now that x value? So they flip spots, okay? So if I want to reflect along the line y equals x, if you start with an ordered pair A comma B, it's going to turn into the ordered pair B comma A. Okay, so an example of that, if I have 3 comma 1, it's going to turn into 1 comma 3. They just changed spots. Okay, this is probably one of the most important reflections, transformations, maybe even geometric concepts that you take from this class that gets applied inside college algebra. Okay, and you've used this a lot. When I want to solve an equation like 2x equals 6, how do I solve for x? Divide each side by 2. Okay, I take the inverse of multiplication, which is division, and I apply that to both sides. Let's say that I had something like x squared equals 9. How do I solve for x? I take the square root, which is the inverse, right? X squared equals 9 is a graph that looks like this. Let's see here. If I look at x squared equals 9, we're looking at something like that for x squared. Okay, equaling 9 would be up here. Okay, does that make sense? So if I put y equals 9, so the intersection would be right there at 3. Does that make sense to everybody? Okay, so what I want to show you right now, I only need the right-hand side of this, so let's do this real quick. Let's go. If x is greater than 0, just show me x squared. Okay. So then the points that I'd be looking for, x squared equals 9. So when y is 9, I'd be looking at this point right there. Okay. And that point is 3 comma 9. When x is 3, the y value is 9. Does that make sense for x squared? You just told me the way that you would solve x squared equals 9 is to use the square root, correct? If I take the square root, let's do it this way first. I'm going to put the line y equals x in real quick. I'm going to reflect this point A on that. Okay? And I'm going to trace out, as I move A, I'm going to trace out what its reflection looks like. That's what its reflection looks like. Does that make sense? Keep an eye on that blue curve. So I'm going to type in the square root of x. And what does the square root of x do? It models that reflection, right? Does that make sense? Okay. So what I'm trying to show you here is that this is x squared. This is square root of x. They undo each other. Okay. If I were to look at, let's go cube root. So if I go x to the third, that is x to the third. Okay. If I were to put a point on that, and reflect that point, and I'll trace it, so end up with that curve. Okay. That is the cube root. I don't know if I have to do it this way. It's x to the 1/3 would be that. So this is x cubed, and this is cube root of x. What I'm trying to show you here is that when you are in equations later on, and you try to solve an equation, you always have to use inverse relationships to do that. Multiplication, division, adding, subtracting, square roots and powers of 2. cube roots and powers of 3, logarithms and exponentials, sines and arc sines or sine inverses. You always have to use the inverse relationships to solve equations. Those inverse relationships are reflections across the line y equals x. Okay? So any function that has an inverse, any function that can be undone by something else, will be a reflection across the line y equals x. Okay? Let's see here. So let's go. There's another line that we're interested in, which is the line y equals negative x. Let's put this point, let's just put a point up here, 2, 4. And let's reflect, same logic, reflect across this line here now. And where does that point go? If it was 2, 4, 2, 4 previously, and now it goes to negative 4 and negative 2. So did they switch spots? It was a 2 and a 4, now it's a 4 and a 2, right? But not only did they switch spots, they did what? Yeah, it changed them from being positive values to now negative values, right? Let's go. Let's start over here with the negative 4, 8. But flip spots, both of them. So we switch the 2 spots, x and y's change spots, and then you make both of them negative. When I make a positive a negative, it turns into a negative. When I make a negative, it turns into a positive, right? Okay. So what we realize here, if we're going to reflect across the line y equals x, reflect across the line, y equals negative x, and you start with a comma b, it turns into b comma a. You flip them, but then they both become negative. And if it started off as being negative, then it's going to obviously a minus a negative is a positive. So that's reflecting across the line y equals negative x. Is that okay with everybody? Here's a quick question for you. If I were to start with it's the wrong program. I'm trying to delete that. Okay. Actually, let's put that on hold. My last statement I was going to make, we'll come up with that here in a little bit. Let's do this. Transformations can be combined. Okay. Now, this is a direct linkage to combining functions later on when you are in college algebra and algebra 2. Okay, so if we understand what's going on here now, it will make things later much easier. Okay, I'm going to show you the notation. Okay, if I have something of the form that looks like this, let's say that I want to do a I'll put it in words first. Let's do a translation, and I'm just put in parentheses here that I want to go right 4 units, down 3, followed by a reflection across the, let's go x-axis. Okay. This is referred to as a composition. When you compose something, when I compose music, when I compose a paper, I'm putting multiple things together to get a final product. Okay. We do the same thing with functions. We can compose functions. There's some notation that has to be done here, okay? The way I've written this by hand says you're going to do a translation right 4, down 3, followed by a reflection across the x-axis. That's pretty straightforward on what has to be done first, correct? Okay. The way that this would actually be written, okay, in math notation is that you would go, you're going to say there's going to be an R, and that stands for reflection. They'll say x-axis, so I'll just write the line y equals 0 here. And then they'll put an open dot, and then they'll put capital T for translation. And since it's going right 4, the x will be 4, and down 3, the y will be minus 3. Okay? And then they'll say of, you know, whatever this shape is. Okay, so I'm just say, I'll just say an A, comma B for the ordered pairs that are here. Okay, now read this. Translation right down 3 followed by reflection across the x-axis. When you read this, and you read it left to right in this scenario, would that make you think that you're doing the reflection first? Okay, and it's reverse. Okay, what happened? This open dot right here is the word composed with, or the phrase composed with, or we can just change it to the word composite, so reflection, composite, translation. And the way that we address this is actually we're going to do a reflection. I'm going to change this into parenthesis notation. Reflection, translation of AB. And the only way that I can really do this composite, because I can't do a reflection on a point that I don't know anything about. Okay? But this I can do because I haven't identified the point for the reflection yet. Working with this is called nested parentheses, and whenever you have nested parentheses, for instance, algebraically, if you had something like this, you would have like 3. If you had 3 and then 5, like x plus 1 squared, like that, or x plus 1, what would you do first in this process if you were trying to evaluate this or simplify it? Say it again. Everything? What's PEMDAS say? Parentheses. So it says identify your first outside set of parentheses, right? And then you run through PEMDAS again. And it says before you start doing that, you got to find the innermost parentheses. So you got to go to those first, right? And you ask yourself, okay, are there any more parentheses? I run through order of operations again. There are none. Okay? So then I go exponents, multiply, divide, add, subtract. And I can't do any of that stuff in here. So if I can't do anything on the innermost set of parentheses, I now work my way on the outside. And say, okay, now I'd be looking at these parentheses here and say, okay, parentheses, got that. Any exponents? No. Is there multiplication? Is there multiplication occurring inside these outermost parentheses here? So I would distribute there first, right? That's what we would do initially based on our order of operations. So what I'm trying to argue here is when we have nested parentheses all the time, algebraically or not algebraically, if we talk about this composite idea, you're always going to work on the inside first. Okay? So I know the R comes first if we read it left to right, but the mathematical approach when we have composite functions is to work from the inside function out. Okay? How does that relate to the way we're going to see it written in our homework? When you see something written like this using that composite symbol, you actually work right to left. You're going to do this before you do that. Does that make sense? Okay. So I'm going to, I don't like moving everything and having a bunch of pictures here. So I'm going to identify what these ordered pairs are. So I'm going to say point A here is, I think it's -6, 2. B is going to be what, 1, 2, should be -5, 7. This point here is -8, 7. I'll call that C. And this point here is -8, 5. Okay, so I've got the ordered pairs for A, B, and C on this picture, right? Okay. What this rule is telling, what this composite rule is saying, is do the transformation first. Okay? So if I start with the points A, B, C, and D, whereas negative 6, 2, B was negative 5, 7, and C was negative 8, 7. D then is negative 8, 5. Okay, if I'm going to do the translation first, so I'm going to put an arrow here, and I'm just going to put a T on top just to tell me that I'm doing the translation. It's going to be A prime is what I'm going to get back from that. Okay, now the translation says you do what to every X value? What did we talk about yesterday? That if that's a positive 4, because I'm moving it right 4 units, right? And that's a positive 4, so I'm going to take every X value and add 4 to them. Does that make sense? So if I add 4 to this, so it'll give me negative 2, negative 1, negative 4, negative 4. Okay? What am I going to do with that minus 3? Subtract 3 from every Y, right? Because minus, you do subtraction. So 2 minus 3 is negative 1. 7 minus 3 is 4. 7 minus 3 again is 4. 5 minus 3 is 2. Okay? So if you took every one of these points and you moved it right 4 units, 1, 2, 3, 4, and then move it down 3, and you got that point, then say, okay, well, how do I get from that point from 0, 0? I go left 2, down 1. Is that what we generated right here? Left 2, down 1, right? Do the same thing with B. Move right 4 units, 1, 2, 3, 4. Move down 3 units, 1, 2, 3. So I have a point right there, and I say, okay, if I'm at 0, 0, how do I get to that point? I go left 1, up 4. Is that what we got? Left 1, up 4? Does that make sense to everybody? Okay, so that translation gets done first. Okay, and it produces those points. Now, what we're going to do, once we have that translated picture, okay, so negative 2, negative 1, negative 1, 4, negative 4, 4, 2, 3, 4, and negative 4, 2. If I kind of graph this, which I said I didn't really want to do because it gets messy, but would you guys agree that that red image is the same as the blue one, just moved right 4, down 3, right? Now what I want to do is I want to reflect that across the line y equals 0. So I want to reflect it across that axis. Okay? So everything that's up here is going to come down below, and everything that's below is going to go up top. Does that make sense? Okay? So I'm going to just look at my ordered pairs now. Looking at these ordered pairs, Control Z. Why does it do that? Oh, I know why. All right, so if my reflection, and remember, we're going to reflect across the x-axis, is going to create, now, I'm taking A prime and reflecting it. So I'm taking that red image that we had and reflecting it. So that's going to give me A, what we call double prime. This will give me B double prime, C double prime, D double prime. And if you remember, if I reflect across the x-axis, if I have a point A comma B, it's going to turn into what? A comma negative B. So the only thing that changes, so I'm going to have the same exact ordered pairs. Negative 2, negative 1. Negative 1, 4. Negative 4, 4. Negative 4, 2. It's the exact same ordered pairs, but the B value, which is our Y, changes signs, right? So this was a negative, it's going to now be positive, right? This was a negative or positive, so it's now going to be negative. Positive is going to be negative. Positive is going to be negative. If I graph those 4 points, negative 2, 1. So I'll do this in black. So if I graph negative 2, 1, which would be right there, negative 1, negative 4, should be right there, negative 4, negative 4, and negative 4, negative 2, would you agree that that black outline shape is now the reflection of the red one? Which the red one was the translation of the blue one. Okay? So these are isomorphic. So that black one is congruent to the blue one, congruent to the red one. But now we've just repositioned it in the coordinate plane. Okay? What I want you guys to understand, and we can do this with GeoGebra pretty easily, is realize that the order of transformation is important. So if I go, I'm going to say A is negative 6, 2. So I know you can't see this right now, but I'll show it to you in a moment. B, negative 5, 7. C, negative 8, 7. And D, negative 8, 5. All right, so those are the points that we provided in the original problem. What I'm going to do here is I'm going to show you 2 graphics. I'm going to cut and paste all of this. Control C. Actually, I think I can do it this way. Object properties, advanced, show in both. There we go. All right, so you guys agree that those are the same, right? Okay. Now what I'm going to do is I'm going to take this and I'm going to move it to the right 4 and down 3. Okay. So the right 4 and down 3. So that's what I was afraid wasn't going to happen. Control C, Control V. All right. All right, so right now, they're the same thing. Okay? If I move this one right 4 units, okay? So it would be, what in the world? Bear with me here. Okay. Control C, Control V. All right, moving right 4. 1, 2, 3, 4, and then down 3. 1, 2, 3. Okay, so she put that point, that image right there. Does that make sense to everybody? Okay. Now, if I ask that to reflect this across this line, okay, so reflect this across that line, that's the image that we got, right? By doing that order of transformations. Okay. Now, on this side, so this is where Order matters. Okay? Let's say that we reflect it first. Okay? So if I take this image here and reflect it across there, so that image reflected across there, now take that and move it 4 units to the right. 1, 2, 3, 4, and then down 1, 2, 3. Is this image right here in a different spot on the X and Y axes than what this one was? Does that kind of make sense? Okay. So what that means is you cannot arbitrarily do these in any order that you want when you see a composite function. Okay. Or composite transformations. Composite transformation. You might see them all different varieties, and when we start getting more rules here in a little bit, when we start doing dilations and rotations, you might see 3, 4, 5 of them stacked on top of one another. Okay, if we do, we could end up seeing something like we do a translation, composite. Let's do a reflection, composite, maybe another. So let's just say a y-axis reflection, and then we'll do a composite x-axis reflection. Okay, maybe the translation is 2, 3. Okay, of some point A, comma B. What that means to us, if we think about the order that we have to attack these, you're going to attack it from right to left. So you're going to start with that. You're going to do that first. Okay. So you'll do the x-axis reflection of A and B, or whatever shape A and B is attached to. Okay, so it might be 4 order pairs, might be 10, might be whatever. Okay, so you'll do the x-axis reflection, and that will give you like A prime, B prime, C prime. Then you're going to do that reflection. Does that make sense? And then you'll follow it up by the final translation. Okay. Is everybody okay with that idea? You always got to work right to left when you see these open circles. Okay, they mean composite or composed with. Some transformations, order won't matter when we do composite. Okay, and what I mean by that, let's say I have a translation of, let's say 2, 1, composed with a translation of 5, 7, and let's just do this with the point 2, 5. Okay, so if I take the point 2, 5. Okay, this translation right here, working from the right to the left, this transformation. Okay, so if this is point A, then A prime. What am I going to do to that 2? I'm going to add that 5 to it, so it gives me 7, right? What am I going to do to that 5 right there? Add 7, so that's going to give me 13, right? Okay, or 12, which is what it really is. So we get 12. Okay, then I'm going to do this transformation. Okay, and that's going to go to A double prime, and it's now starting with the 7, 12 instead of the 2, 5. So what's that 2 going to tell me to do to the 7? Add 2, so it gives me 9, right? What's that 1 going to tell me to do with this 12? Add 1 gives me 13. Is that okay with everybody? So that's going right to left. Let's do it this way. Let's say I start with 2, 5 again, but now I do this. Okay, what's that 2 going to tell me to do to this 2? Add 2, so it gives me 4, right? 1 and that 5 gives me 6. Now, this 5 and 7, what's 5 plus 4? 9. What's 7 plus 6? 13. Are those two the same? But do we do it in different orders? So what's that tell you about the ordering of translations? They're the same regardless of the order, right? What property is that? Commutative. Okay? Composite translations are commutative. Okay? Not all transformations are that way. Okay. Now I also think about this. What did you took 2 and you added 2 and added 5 to it, right? Okay, so this composite transformation of 5, 7 is exactly the same thing as a singular transformation, or translation in this case, of 2 plus 5, which is 7, and then 1 plus 7, which is 8. So the translation of right 7 and up 8 is the same as the composite of right 2 up 1 followed by right 5 up 7. That kind of makes sense? And you guys know that from anything in the unit, or the coordinate plane that we've ever dealt with. If I want to go from 0, 0 to that point right there, can I go up 2, right 1, up 1, right, however many, up 2, right 1, up 1? Will that work? Does that get me from 0, 0 to whatever that point right there is? But doesn't it make logically more sense to go all the way to the right as far as I need to get underneath that point? I don't know why for this class these markers don't stay where I want them to. Go all the way to the right, that distance, which is the sum of that one, and that one, right? That's adding all the x's up. And then you go straight up, which is in the sum of that one, and that vertical distance. Okay? So when you move around, this is called a rectangular coordinate system. When you move around the rectangular coordinate system, left and right, up and down, you are using potentially composite translations. Okay? You may have seen, or not seen yet, I didn't give you your homework yet, but you will see in your homework today something like this. They'll say, take the point, let's go to point 4, negative 3. And they'll ask you to reflect across y equals negative 8. Okay? And what that will really look, so that's it written in words. What it will really look like is there'll be the capital R, subscript will be y equals negative 8, so that's a reflection across the line y equals negative 8 of the point 4, negative 3. And they'll ask you, well, what is that? I'll give you a box, and I'll ask you, what is that ordered pair? Okay? I think an image is most appropriate here. Okay, I'm starting with the point 4, negative 3, right? So 1, 2, 3, 4, 1, 2, 3. Doesn't have to be the scale, but you want to be in the right quadrant, obviously. Now I'm going to reflect across the line y equals negative 8. What kind of line is y equals negative 8? It's horizontal through what value? Negative 8. So that's negative 3, 4, 5, 6, 7, 8. Okay, so this is going to be essentially my axis of symmetry. That's going to be the line that we fold this entire plane on. And if I fold on this, doesn't it make sense at that point it's going to come down here somewhere? Okay, now distance-wise, okay, that distance right there is how big. If this is y equals negative 8. It's 5, right? Okay. And the way we find that, remember, the way we find the distance between two things is I'm going to take the negative 8, which was that value right there. I'll take negative 8 minus negative 3. And I take the absolute value of that, right? And that's going to give me, in this case, 5. Okay, so that distance is 5. So when I reflect, doesn't that distance have to be remodeled right there? It has to still stay 5, correct? Now help me out here. Just think logic, because I don't want to do a whole lot of math here. What's the x value of this reflection point going to be? It's going to be 4. Has to be the same as that x value, right? Okay. Now, we said that this distance was 5, right? That distance was 5. What can I can do it one of two ways. I can either start with that value there and add what or subtract what from it to get the ordered pair or the coordinate for this ordered pair down here. Subtract 10 from it. -3 minus 5 will drop me down to the line of reflection, right? Minus 5 more will get me down to this point. So I've subtracted a total of 10. So it would be twice that distance right there, right? 2d, if we call that d, this would be 2d. So -3 minus 10 gives me -13. Does that kind of make sense? Now the reason I show you that kind of structure is because what happens if I do this? Let's take the point. Let's do a reflection across the line. Let's go x equals 12 of the point. Actually, let's do it this way. Let's do x equals 120 for the point of -400, 776. What's the issue with those values I just chose? You can graph them, but it's going to be very tedious to graph them, right? Okay, you don't want to draw out to 120 to draw your vertical line to the right, and then you got to go to -400 and 776 in the x and y directions to find the point. Okay, so let's see if we can draw a picture that's not to scale, but would help us understand how to find this ordered pair. So if I take x equals 120, so that's going to be a vertical line on the right-hand side of the y-axis, right? It's going to pass through 120. So that line right there. That blue line is x equals 120. Okay. Our point is at -400. So if this is 0, 0, -400, 776, right? -400, 776. Okay. When you reflect across this blue line, that distance right there is going to be captured over here, correct? It's got to be the same. That being said, it should be easy for us to determine what the y value of that point is. What should be the y value of that point? Still got to be 776, doesn't it? Okay. 776. Okay. Now, how far is that distance right there? It's 520. Good. Okay. Because from the red line, which was the y-axis, to here is 400, and this is an extra 120, right? So that's 520. So then how far is that? Remember the axis of reflection, the axis of symmetry, it's 520 to go to that point, so it doesn't have to be 520 to go to that point. Okay. So now to find this coordinate, okay, what do I need to add to this x value? $520 will get me, if I add 520 to it, it's going to get me right there. I'm going to add 1,040. So -400 plus 1,040, whatever that turns out to be, will be my x coordinate from that point. Does that kind of make sense? So you can use that understanding of working on a small scale, and on a small scale we can actually count, but then use those relationships that you realize there to help you work on a problem that has a very large scale, okay? And it's very likely you'll see something like that on your homework in the next couple days. Does anybody have questions on reflections and translations? Anything about composite functions that are confusing? I'm going to open an assignment for you to give a shot at. Over the next 3 days, remember they're all 2-hour delays tomorrow, the next day, and Friday. But what's nice for us is that we actually have full class periods, right? So we got 3 full class periods here that we can work on. I want to work on rotations and dilations, okay? And then next week we'll get into probability. And then the following week you'll take your test. You'll all get 4s and 5s, and we will be on to the end of the year.